Our today's speaker is Professor Aida Todri-Sanial. Let me introduce her today. So she is now a current full professor at the Eindhoven University of Technology, Netherlands, and director of the research for the French National Council of the Scientific Research, CNRS. Professor Todri-Sanial was a visiting fellow at the Cambridge Graphene Center and Ulfson College at the University of Cambridge, UK. Previously, she was an R&D engineer for Fermi National Accelerator Laboratory, Illinois. She has also held visiting research position at Mentor Graphics, Cadence, ST Microelectronics, IBM, TJ Watson, and her research interests are on emerging technologies and novel computing paradigms such as physical computing, neuromorphic, and quantum computing. She is the recipient of John Braden Fellow in Engineering in 2009, ACM Distinguished Speaker from 2016 to 2018, CEDA Distinguished Lecturer currently, and CNRS Bronze Medal Coordinators and participants in several EU projects such as NeuroON and many other projects. She is also the recipient of the prestigious NWO AINED Fellowship and the ERC Consolidating Grant. She was the general chair for the 2025 edition of the DATE conference. And let me welcome Professor Todri-Sanial. So floor is yours, Professor Todri. And for this audience, you can put your question into the chat box. Feel free to add your question. And also you can hold some questions for the end. That's fine. And if you can write it and I will go through the chat box and I will try to repeat the questions at the end of the talk. Thank you very much.
Thank you. Thank you for this very nice introduction. And I'm very honored also to have this opportunity to give this talk online as a CEDA distinguished lecturer. And welcome to everyone. Good afternoon or good morning, depending on which time zone you're coming in. And today I would like to spend a little bit of time to give a little bit of an overview to what it means physics-based computing, especially with electronic coupled oscillators, and a little bit of perspective. So what are the challenges for this computing paradigm and what's coming up next? So first, I would like to introduce my team. I think it's important to also see a little bit the people behind a lot of the work that I'll be presenting throughout this lecture. So I'm leading the nanocomputing research lab at Technical University of Eindhoven, and there are three main clusters in my team. There is the algorithms and information theory, so a lot of the focus on statistical physics, but also machine learning and algorithms, and there are various PhD students involved. And a lot of the topics are from physics-based computing, also the topic of today, and then thermodynamic, adiabatic, sense to compute. And on the middle core, which is also the part of the hardware design, it's focused on integrated circuit design. I'm also part of the integrated circuit group here in electrical engineering, and a lot of our focus is toward analog, mixed signal, and digital design. We also have some work in the materials and devices. This is more exploratory in the clean room, where we're looking into functionalizing materials and also getting certain memory, but also sense and memory type of functionalities with 2D materials. So this is also something that we have recently started in the group. I would like to focus today a little bit more about this novel computing paradigm, so physics-based computing based on oscillatory neural network, and also some of the problems and application domains where this new computing paradigm can bring some new innovation, but also some advantage. And I'll also talk a little bit about the various implementations and technology choices that we have taken in my lab to implement this new computing paradigm, and follow it a little bit more with a perspective, and also to see what are the challenges to be overcome for more scalable hardware. I'd like to introduce it first with the demand, or the growing demand on energy efficient computing. And we see computation pretty much in every domain, in every part of our, not only the way we work, but also the way we live, the way we entertain, and also the way we actually consume new data and also generate new data. This is from the way that we are interconnected. So this is from for example, from automotive in the way of mobility, but also from the way of how we actually are processing data from the cloud to data center, mobility, healthcare, but also from the grid. So in terms of how we actually making real-time decisions on the grid when we are switching from one type of source of energy to the other. And also about climate, dynamical in a way, it's a dynamical type of a system that has some heavy duty, I would say, mathematical formulations that need to be understood in order to be able to have some prediction in real time, but also prediction in long period of time. What is important about all of these type of problems is that underlying core or the challenge with all of this type of applications is the mathematical problem or the analytical formulation that these applications require. The essence is all of this type of application require some more complex mathematics, as I mentioned, from dynamical system, but it could also be for more partial or ordinary differential equation. So the question is, rather than trying to target this type of applications or computing demand with the current CPU, GPU, or TPU base, which is very good at performing arithmetic operations, this kind of applications, as we'll see, are more toward performing more complex mathematics and calculus. So from ODE or PDE. So you are looking for a hardware that is performing natively all of these hard mathematical formulations or problems that you want to solve. And as we are also seeing from the trend on exponential data, so we have an increase in data volume in zettabytes coming in the coming years. And we are also seeing this from the energy growth. And a lot of the energy growth will become from generative AI workloads. And this also requires that the hardware where we are performing all of these workloads and all of these applications that are running ubiquitously throughout various domains require also a rethinking of the computing hardware itself as well. So that's why the motivation behind this work is to look into novel computing hardware that is also more prone to what the mathematical core or the mathematical problems that these applications require. And this is barely unsustainable without any significant computation innovations in the hardware. So the goal is to bring closer this mathematical need or these problems, what they require, and into closer to the hardware. So rather than trying to map these problems into arithmetic-based computation, what about bringing the hardware innovation that these applications require, which is natively very complex calculus type of computations from gradient descents, partial differential equation, integration, and so forth. So that's the challenge, but also that's the motivation toward novel computing paradigm. And the computing paradigm that I will be talking about today, it's let the physics perform the computation. So this is a departure from a state machine type of computation on the Neumann computing hardware, where we have this continuous shuffling of the data between processing and memory. So this is very sequential in a way, and also a state machine-like type of computation. So the goal is to go to more recurrent or something that mathematically performs the core equations that the algorithms require. And that's where we are trying to bring in a new hardware implementation ideas for physical computing, which the network is a complex network. It's a nonlinear dynamical network that intrinsically performs a mathematical function. And in our case, this is a gradient descent. And the gradient descent or the evolution of this dynamical system also presents a specific behavior to the problem that is embedded into them. And I will talk a little bit more about this more in depth. So the goal is to see that we are stepping away from a state machine-like computation toward more a dynamical system type based on computation. And we are really trying to harness and to exploit the dynamics of these complex networks. Typically, they are very much utilized to represent complex networks in biology, in finance, but also in microsystems. So looking into them in a mathematical way to reproduce or to understand how a problem of interest can be embedded, so can be mapped into them, and the evolution of these dynamics actually telling you something about that problem. So for example, in this case here, in this graph, what we are showing here is the energy minimization, so this gradient descent of the problem, that also tells you something about the output or the solution of the problem that was embedded into it. So that is the type of computing paradigm that we have started to look into over the various various generations of PhDs, but also projects, in order to be able to implement this not only mathematically and analytical solution, but also into hardware. To give you a bit of intuition, and I think many of you might have seen this type of experiment where you have metronomes that do synchronize when they randomly start. So you can also look into these short videos where the metronomes can randomly start any given time. And also this is the bass. Also the movement of the bass allows, after a certain very short amount of time, a synchronization of metronomes. Well, the same principle is also applied to coupling oscillators, so the dynamics of coupled oscillators. You can think of it as a perceptron, so fully recurrent neural network, where each node is an oscillator, and they have a very naturally, intrinsically, these systems are very good for associative memory, similar to Hopefield neural network. The difference from Hopefield is in Hopefield we don't have an oscillatory type of vertex, but we have more of a binary representation. And the difference also brings more degrees of freedom of the encoding of information. So now we have an oscillator, which in a polar plot can have a degree of freedom from 0 degree all the way to 360, so full circle. So there is more than just binary. So that's the difference between Hopefield. But similar to Hopefield, you can perform this associative memory, meaning that you can give a fuzzy image and you can retrieve in a very short amount of cycles what was memorized into this circuit. And importantly is that, for example, in this image, each pixel represents an oscillator. And we'll talk a little bit more about this encoding of the information on black and white or grayscale. But important to mention that all the computations in this dynamical system is performed via the phase. So rather than time domain, I will mention that a little bit further down the line as well, we have departed from time domain computation, but more toward understanding the frequency, the collective frequency of these coupled oscillatory neural networks, and the phase relation between oscillators. And also the information is encoded as the phase relation. What does that really mean? So if you look into two of them, let's take the example of two coupled oscillators, and let's make the assumption that they are positively coupled. And you have two specific oscillators individually, and this strong coupling brings them to be completely in phase, and that is a 0 degree phase difference between these two signals. In a pixel, you can think about as two white pixels. Similarly, if you now have these two oscillators, but they are now negatively coupled, you'll also see that the phase degree between these two signals is 180 degree. That also allows for this encoding of 0 to be a white and 180 degree to be a black pixel. But as you can imagine, we can engineer, or we can change these coupling weights in such a way to have more degrees of freedom. So not just binary 0 and 180 or black and white, but more refined phase differences between oscillators to allow more fine grain or even more embedding, so more multi-bit resolution into the system. So it's an interesting, so it goes beyond binary. So because it's also being an oscillatory neural network, so an oscillator, it's an analog in nature. It allows more continuous phase modes that you can also even measure accurately and allow to encode information in the phase space. I would also like to say a bit about the history of coupled oscillator-based computation. This is something that initially was observed by Huygens with synchronization of coupled pendulums back in the 1600s. And at the time, he was observing the two tower clocks in two nearby villages and the synchronization of these two tower clocks, even though in a distance. But in the 1950s, where the foundation of computing from von Neumann and Turing were set. In the same time, we have quite a lot of analog-based implementation of oscillatory neural networks, and also some digital logic-based implementation. This was very first from von Neumann and Goto. And this did not really go beyond than that. So for that first decade, and the reason was because digital took over. But there were the very first initial ideas on how to use oscillators for computation. In the same time, we have the evolution, or quite a lot of the statistical physics algorithms that became, so for example, with Lenz and Ising, Metropolis and Hastings, Kirkpatrick and Ackley, that actually started to develop the very first algorithms, or the very first principles behind the spin configuration in a system, the random numbers convergent of distribution, the simulated annealing, which is widely applied, and learning models for Boltzmann machines. So this, in a sense, also developed in parallel. And we also, in parallel to all of this, we also have the neuron model and the neural networks. From the neural networks, we started with the very basic perceptron and the layered neural networks, from artificial firing, also to Rosenblatt, Minsky, Peppard, and Hopfield. Hopfield was one of the stemming neural network that it's closely related to coupling or oscillatory neural networks. And this evolution, or this progress on neural networks, along with a neuron model. It's also important to mention that the neuron model on these neural networks also changes the dynamics of the system and also the computational capability of these systems. So we had, at the same time, we had Van der Pol, Hodgkin and Huxley, Winfrey. Importantly, you will also see later on the Wang, so the evolution on Kuramoto, Endo, and Hoppenstad. And the seminal work in early 2000, bringing the weakly connected neural networks together with the Zhikevich model, so the oscillatory, brought this seminal work of coupling or computing coupled oscillators, and the dynamics expressing mathematically the dynamics using the Kuramoto formalism. And they were using this for performing pattern retrieval. So this was the very first sort of seminal work which brought together not only a lot of the developments that were done from neuron models, the neural networks, and statistical physics, but now to seeing all in one used for computation. So they weren't only sort of, in a sense, standalone models or theories, but now they were, in a way, consolidated all of this knowledge from statistical physics, so the spin configuration, the neuron model, the Kuramoto formalism, and Hopfield, into one unified ODE, so ordinary differential equation, to be able to explain the dynamics or what actually happens when you couple oscillators and what is their computation capability, especially for pattern retrieval. So this was the first seminal work to stem and also to bring a lot of momentum to the field. From there, what we are seeing is quite a lot of different works on machine learning that took over, and a lot of also the works with my PhD students, where we started to look into it from also classification, pattern retrieval. We also, there is quite a lot of work from the community, but also from my own lab, looking into combinatorial optimization problems that can be mapped into these networks. And then more in the recent years, we're seeing into image processing, but also more into the hardware development for this type of computing paradigm. So this has been an interesting developing field. There is quite a lot of active groups internationally in the US, in Europe, and also in East Asia, looking into various technology choices, various also problem embedding, and benchmarking this for interesting use cases and applications. In our work, so it's important to mention, right? So where it all started from. So from the seminal paper from Hoppenstad and Zhikevich, and it's important to give a little bit of an important description of the ODE, so the ordinary differential equation for this ONN dynamics. So the system looks very interesting. So it's an ODE where you have the phase dynamics represented as a function of the natural frequency, which we most of the time considered they are uniform coupled oscillators, but then this interaction matrix, which comes from the coupling matrix, but also depending on the waveform function of the oscillator. So this is also the oscillator model that you use. And this is typically a 2-pi periodic, so it can be odd or even, that describes the phase response curve of your oscillator. So this ODE, so this order differential equation that we use to represent the coupled dynamics, can also be adapted in such a way or to represent different type of problems. So this is also later on you will see how that is how this ODE is used to represent the cost function or to build the link toward a problem of interest. Yeah, so it's also important to mention what is the Neumann model, right? So the simplest Neumann model, which also this ODE can be represented via the Kuramoto formalism for the coupled oscillators using a sinusoidal Neumann model. But there can be much more different type of Neumann models that we have explored. So the simplest one, as I mentioned, is a sinusoidal. Why? Because it's periodic and it's much easier to compute, but also to implement into circuits. But there are also more nonlinear type of oscillator models that can be also very interesting, such as, for example, this is a second order van der Pol. It's interesting because it represents multi-frequency and also that it represents multi-ways of encoding information because each frequency can carry phase information. Then we also have looked into Fitsu Nagumo, another order, and also a little bit more complex into Izhikevich model. So going really from sinusoidal toward real neurons that are more biologically plausible to be able to bring in that complexity and to the system. Because also the dynamics of the network become more chaotic as we are also utilizing as we go beyond sinusoidal oscillators. So this is interesting as well for computational capability of the system. So the nonlinearity actually it's a very nice added feature to these networks, remaining simplistic in their form, in their topology, but by increasing the nonlinearity on the oscillatory models and the coupling eventually brings more richness to the dynamics of the system, which is very interesting for certain problems. Yeah, so what kind of problems and application domains that we have also looked into? We have looked a lot into associative memory problems. Why? Because this is intrinsically coming from the associative memory behavior that these networks can perform, similar to Hopfield. So you give a fuzzy input and determining how these coupling coefficients have via different learning rule like Hebbian. But not only, there are other type of learning rules, incremental learning, local rules like Storkey or Dritty-Oper or others. You can obtain in a very few amount of cycles the memorized patterns. Also for image processing, this is very interesting for edge detection or also segmentation, which can act, so the ONN can act as a filter on a larger image to be able to extract information. And also for combinatorial optimization problem, there are the class of problems which are very resource demanding, and for certain problems, actually, it's important to bring some innovation in acceleration on how to solve them, such as traveling salesman problem, graph coloring, max cut, or satisfiability problems. So these are, in computer science, there are a class of problems, but they're found in many industrial domain as use cases. Yeah, so these NP-hard problems can be found in every domain, from personalized medicine, scheduling problems in factory, but also in more in mobility as well. In grids, as I mentioned earlier, also to switch from one type of energy source to another, and even in VLSI chip routing as well. So in computer science, there are the 21 NP-complete problems, but also they have this practical application that they can found in different domains, and providing solutions for acceleration for these type of problems it's quite important. And I also want to mention that the hard problems or the computational complex problems are the combinatorial optimization, But also deep learning. Learning is also training and also solving this linear partial and differential equation. So what we are trying to also explore here is that this type of dynamic, so computing with dynamical or complex networks also allows certain mathematical formalism that is so suitable for solving linear and partial differential equation, because intrinsically this complex network is a PDE, it's an ODE by itself. And it's also interesting for deep learning because you're optimizing for something, and similarly for combinatorial optimization problem. So that also brings that practicality or feasibility to explore a different type of class of problems. So the implementation choices, I would like to start first from the lower part of the computing stack, so from materials, devices, towards more into CMOS-based or silicon-based solutions. So from the novel material and devices, we have spent quite a lot of effort and over the years to look into a low-cost oscillator based on a phase change material, more specifically vanadium dioxide. And for the coupling elements or CNAPs, we also used bilayer Hafnia, and this is in collaboration with the colleagues at IBM, where they developed this type of technology. So using metal oxide, conductive metal oxide layer, to be able to have a very analog-like conductivity change on the device, which is very interesting for the synaptic element. On the Neuron, on the oscillator, using a VO2 oscillator with externally coupled resistance and capacitance, provides a very low cost and energy efficient oscillator. And we have looked into it, and we have seen that indeed this technology, so these emerging technologies, provide a suitable platform as well. Yeah, so this is from the VO2. So this is a phase change material that undergoes lattice change, the phase change due to Joule heating, and that also causes, so when the heating and the cooling, that also causes this self-oscillatory behavior on the device, which externally coupled with RNC, you can obtain a very interesting self-oscillatory device. So these are based on crossbar type of devices as shown here. And this is also closely in collaboration with colleagues at IBM in Zurich. In terms of the going further to the more array-like, or to see how this would perform into ONN using this type of novel materials and devices, we have looked into a crossbar implementation with this ReRAM devices, and also with ring oscillators, external ring oscillators. And as I mentioned earlier, this conductive metal oxide Hafnia device has a very interesting behavior, which also allows to have different, so not the range of conductivity or conductance changes, that is also suitable for the type of coupling element we would like to implement on ONs. We have done some proof of concepts development with them using 1T1R ReRAM arrays with ring oscillators. So we've performed this sort of a proof of concept on using their die with our PCB implementation of ring oscillators. And now we have taken this more into an integrated platform with CMOS-based ring oscillators coupled with 1T1R ReRAMs. And this is just a little measurements to show, for example, initialization of this network, a small network, initially starting random initial conditions, so the phase, and then in a couple of cycles, you can see in 3 cycles getting back to the memorized, what was the memorized, depending with respect to the ReRAM coupling elements, to go to what was the memorized pattern. So this is an interesting development, and we are continuing to work closely with the colleagues in the framework of Fast Track project to bring this CMOS and ReRAM co-integration together. On the chip development, as I mentioned, we also do several tape-outs over the years. The PhD students have developed several tape-outs, like in 65 nanometer. This is a very mature, but also inexpensive, very cheap node that we can regularly tape out test structures and different type of architectures and make various measurements, and also look into the new features that we bring to the ONN. And these are some of the various tape outs over the years. And the challenge, or at least the innovations that we've been trying to show forward, is to utilize, for example, a saturated Kuramoto model or phase shifts or control phase shifts into the coupling elements. And also this is bringing more closely, as I mentioned earlier, the heterogeneous integration with ReRAM devices. So we have looked into also the topology. So these various tape outs have also allowed us to, as a proof of concept for the various topology for how to implement and how to also control the dynamics of the network. So I will take one of them. So this is one of the work from one of my former PhD students, where he looked into a mixed signal ONN architecture, and he developed this saturated Kuramoto oscillatory neural network where the oscillators are in dual mode, so they are in a mixed mode, and all the connectivity or the coupling is performed digitally in order to allow better scaling, but also better control. So there is no time slack or time constraints that are not being met. So this was an interesting first type of architectures that we implemented. And so, yeah, this shows a little bit the chip floor plan and also the symmetry of the design, 8 oscillators and a current bias in the middle. And I'll show some of the also explorations that we did. So one of them was solving the TSP traveling salesman problems with ONNs. So this is initially what the problem requires. If you use binary phases, Ising, this would require n square type of oscillators for the distance, but also for, so these are the cities and these are the distance. So if you look into how would you map this would require n square. So this is very inefficient. And what we have done in this investigation, in this work, is to show that you can embed information in phases. So that means phase now represents the distance between cities, and this also reduces the complexity of how would you embed TSP to ONN. This is very interesting, and we have also shown, so this is how the energy cost function of the system would look like. And to visualize, you would have, for example, a bunch of cities that would be arranged around the polar plot. And this will also tell you a little bit the shortest path, or initially they start randomly, and then this is the final, when they reach equilibrium, so the steady state, and also to get the overall distance, or what is the distance for visiting, or the order for visiting as well. So in a sense, this is a first sort of motivation to look into the added value or the advantage of using coupled oscillator, which reduces the problem complexity, but also trying to exploit phase as a way to encode information, in this case, the distances between the cities. We're also looking into the modular ONN chimera graphs, where you have a lot of this smaller, so you can think about a large TSP, which can be broken down into smaller TSPs using this modular ONN approach. So this is also something that we have looked into over time. Another one which comes from MaxCut benchmarking, which is a very simple bipartiting or cutting the graph into 2 parts by maximizing the cut. And we have also done this on our chip measurement. So the student did a lot of this measurement, and it was a 16 node or 16 oscillator type of topology. And here we are looking into the accuracy, but also the time to solution. And we also in simulation look into larger scale systems and comparing with the circuit. And we are seeing here this trend, which increases with the size of the problem, but not in the same scale. So what we are seeing is this speed up, and in not only the speed up, but also the trend, which seems to be in a logarithmic trend. And this is also a very interesting feature to be further exploited, which we are looking into now into different larger system to see how this oscillatory neural network would be of interest, or at least see what is the complexity that this system exhibits for this type of problems, so NP or combinatorial optimization problems. Other type of applications we have looked into is also more into, as I mentioned, image, but also AI. So we have looked into using ONN as the processing for the image, but also for sensory data. We have looked into small robots, so putting sensors around it, so time of flight, and also performing heterogeneous or heterostructure associative memory to be able to get this line or edge detection. I will talk a little bit more about one of the recent use cases where we perform a digital ONN, and we implement this on a recent use case for image and sensory data processing. So on associative memory, what we have seen over what we started with, so this is some of the earlier work, we implemented first a digital ONN, and we started to perform associative memory from getting data from the camera. And this was the very first, we implemented this on a zinc board, and this allowed to kind of understand the behavior of the system for image processing in a real time to see if this can be deployed on another type of edge AI type of application. The next thing what we also tried is for obstacle pathfinding and obstacle avoidance. Initially, this robot has sensors throughout, so 360. And the goal was to have this robot without any training at all, but to train based on the real-time scenarios, so to avoid obstacles. So this was also to do the real time. So how many scenarios this ONN would require to be able to learn to avoid obstacles or hitting the wall. So this was also something very interesting work that we have worked on. And more recently, we have, I'll talk a little bit about this real-time multimodal sensor processing on a flying drone. This is something that we developed in-house. So it's a small drone, very lightweight, which was the main constraint. And how we map this is to get information from the sensors, which are embedded as a vertical or as a thermometer encoding. So when it's black, for example, shows that there is an obstacle or there is an obstacle in front of you. So that means this is not a viable direction. So you need to choose another direction. So you can think of here, for example, this drone has sensors 360, but also up and down for lateral and vertical. So for example, here from 0 to 360, you can get this map to see what are the obstacles in black and what in white are the directions that this drone can fly. I'll show in a moment a little mini video from it. And you can do this in a as you can see here, very small ONNs, so not very large. So these are 24 to up to 40 oscillators on an FPGA stick that can allow to be lightweight, but also something that can make this real-time decision, and different type of sensors. So time of flight, but also some of them can be from camera. So it's different type of a multimodal system in the same time, but all being processed via pattern recognition via ONN. And here is a little bit more detailed view. Because it was a very lightweight, we also had to do some cutouts into if you can see, into the board in the PCB that we developed. And you can see there are 3 layers. So there is the controller, but there is also the FPGA. So this is the FPGA stick. These are all the sensors throughout. So there is throughout, you can see here all the 12 sensors, but there is also up and down sensors, as I mentioned. And here, maybe I can try to see if I can show. Yeah, so this is a tabletop, just showing if you put an obstacle and the direction that the drone would take. And this is another it's a little bit heavy still, but it's still where aerodynamically we need to be a little bit better at our component choices. But just to show that it's a very low cost solution. And this is a digital implementation of the analog ONN, but can be very interesting as well for sensory processing near the sensor, and also near the camera. So this is something very interesting as well. Yeah, so going further, maybe also time-wise, to leave a little bit of time to answer some question. There are quite a lot of challenges going forward in this. So I gave you a little bit of an overview from applications. So as I mentioned, from combinatorial optimization problem, from AI, ML, and also from the system, from the design perspective and the technology choices. But going forward, there are quite a lot of interesting challenges from also the algorithms. We still need to, I think has to be some co-development from the physics community, computational physics community, and the suitable algorithms that can be implemented on the circuit. So there has to be a little bit closer co-integration between circuit design and also with the algorithms. So coming from, especially from the physics or computational physics domain, that allows to have a better embedding of these problems, a better embedding of these algorithms. So then the hardware actually does what the algorithm needs. That's, in a sense, the new future, I think, challenges that we need to overcome. The other angle to all of this is the developments from the various materials, devices, the technology choices. I think what we are seeing is that certain capabilities are also much more easier to implement on certain technologies like in ReRAM, but also in 2D materials or 2D TMD based devices. So that can be multifunctional devices that can also perform sense and this interface to compute a much more seamlessly and also energy efficient way. So I think there is quite a lot of potential as well to look into novel hardware platforms as well, that this computing paradigm can be more advantageous as well. And of course, from the benchmarking from the algorithms and applications, I think we also require the community-wise as well. Maybe this is also a call for community to have maybe standardized benchmarks where we can also see how these various different computing paradigms, not only physical computing, but also other one, thermodynamic, adiabatic, reservoir, sort of standardized ways to kind of understand how, what are the advantages and disadvantages or pros and cons of these various new forms of computation or models of our computations that we are developing. So there are challenges on all four fronts, but the heart would be, what would be the technology? So the hardware design to be able to build these accelerators or processors based on these new computational models, and how to scale them, especially the scalability, given that oscillator uniformity, variability can also be playing a role into the robustness of the design. So this remains still to be further investigated, and there are quite a lot of interesting problems there from a hardware circuit design perspective. So maybe given the timing, maybe I will wrap up there to give a little bit of time to answer maybe some of the questions that you might have. But thank you for your attention.
Thank you very much, Aida. It was an amazing talk. So I think I can read out the questions, but do you want to also read? Can you see the Q&A?
No, I cannot see, but maybe I can stop
Okay, no
sharing, then
problem.
I can be able to
No, no
see
worries.
them. Is
I can
that
read.
okay?
Yeah, it should
Oh,
be
okay,
fine.
okay.
But I can also read, and yeah, you can unshare it. Yeah, that should be fine. Yeah. Thank you very much, all the participants. Yeah. Uh, Unfortunately, I think I didn't introduce myself. My name is Mohammed Al Farouk. I'm a professor at the University of California, Irvine, and I'm moderating today's distinguished lecture series. So the very first question came about the EDA tools. So they're asking that if you are exploring any EDA tools for this mapping these ONNs into ICs, and if you there are a couple of groups in Berkeley, I think you also know Jayjit is working there, and some of the PhD alumni from his group are working. So the question is that what is the current state of the EDA tools and whether you are using all those EDA tools, and yeah, can you comment on that?
Yeah, so that's a great question. The EDA is also evolving very fast in the framework of AI, right? And also agentic AI that is really speeding up a lot of the developments in that domain. So the EDA tools that we utilize in our group, and a lot of also my colleagues in my group, we are very much circuit design platform cadence based. And I think for the kind of design we are doing on CMOS platform, the cadence or synopsis for that matter, they're both very suitable platforms, and we utilize them very and I think you can perform quite a lot of interesting work, and you can explore quite a little different topologies, architectures, Monte Carlo analysis to understand how your system or how your network evolves in the framework of any mismatches. So I think that the cadence, I think the current EDA, it's very it's very suitable for what we are trying to. But I think what we can be also interesting can ADA and maybe this optimization solver hardwares, can they also at some point, will there be a moment of synergy? And I think maybe also EDA can benefit from some of these optimization solvers because they can also speed up maybe all of these problems from placement, from routing, from congestions, from also design exploration, especially when you go in 3D. So maybe there is a synergy point there. So the EDA, we are users of EDA, but I hope EDA can also see potential in what we are developing. So I think it's a two-way street. So I don't know if the jury is still out, but I think it's a very interesting because also they also are looking for better and better solvers because the problems are getting more complex. So maybe there is an opportunity there for this type of solvers we are developing. So optimizers, so the optimization problems.
So I think Giovanni has multiple questions, but let me see some of the questions that he was asking, that if you can explain a little bit how to map the analog ONN to digital ONN. I think you tried to explain a little bit on FPGA especially, such that the
Yeah.
digital ONN can be implemented in FPGA. I think he wants some a little bit details. And also if you can, okay, go ahead and answer this thing and then we can
Yeah,
ask.
so the digital, so ONN, so let's say it first, the ONN intrinsically is analog, right? So that's the nature, it's analog. We are focusing a lot on the analog design, and that's our core focus. The digital part of it, it's a nice proof of concept to see if you represent the oscillator as a clock, right? So it's a square wave. Now, Izhikevich formulation of the phase dynamics is valid for sinusoidal, sawtooth, square waves. So it's still valid. So it holds. So we have that foundation, so theoretical foundation to know that even though you represent the oscillator as a square wave, you can still perform a meaningful computation. So theoretically, you have that confidence to exploit square wave type of oscillators. So that's our analogy. So I hope that gives a little bit of an insight. So what we are doing in FPGAs or digital ONN, we are using it as a clock, and we are performing a lot of clock-based computations. And you can also look into a lot of the published work we have done on this topic to give a little bit more insight on the architecture itself, but in the thrust is there. But it's not the true ONN behavior. So we are using a discretized version because it's easy to implement on FPGA and you can deploy it on robots or drones, or you can do a lot of cool, interesting use cases. But the true advantage of it's on analog, and that's where we are focusing a lot. I hope that answers a little bit the question on the digital part.
Yeah, I think you give some insight. I would recommend definitely read those papers that you basically
Sure,
point
sure.
out. Yeah, that will be wonderful. So Giovanni has another question. I think this is interesting conversation that he's asking that you spoke about multiple things: computational physics, IC design, applications, algorithms in AI, ML. We see a lot of light and material and devices definitely.
Yeah,
So
the 4
I don't know whether he's graduate student or a faculty, but he's saying, how do you recommend we use system technology co-optimization? So how these things has to be co-optimized basically eventually, because scaling is a factor. You already mentioned in your talk that we are not there. So we need to make complexity. We are working, but the complexity we cannot handle large complexity. So how do we do basically system and technology co-optimization?
So I think there are many angles to it, and different groups are exploring different pathways. I am loving the some of the, I don't know, in the community, people are trying to do FPGA farming. So that means you have a small ONN on FPGA, and then we farm it. That means we have a bunch of them, and you can build a bigger system. But yes, then you have other problems, the latency between FPGAs and boards, and the problem is shifted elsewhere. You see, it's shifted on the connectivity and synchronization of the network at different time scales. So it becomes a different problem. So that's one angle, right? And I think that's suitable. Still, we have some more integrated solution. the true, as I mentioned, behavior inherent is analog. So somehow, if we know, or at least if we need to have some good design, it's an art, right? Custom design, it's an art. So till we have a scalable ONN that it's robust and reliable, and maybe we can make it modular, similar to what we do FPGA farming, maybe that's where I see some interest. So that means maybe building robust standalone chiplet type, but now we're going to a larger scale to map our problem. But again, the challenge is the moment you have different time scales on chip, intra chip, and intra boards, you know, that those different time scales change the computational dynamics. And we don't have yet the theory to guide us what happens when we have these different time scales into our network. Does it compute as it should? Or maybe do we solve the problem partially and then constitute the global problem from those partial solutions? The jury is still out, right? But I think there are many pathways. But it seems like modularity might be an eventual next pathway. And I think the advancement in advanced packaging, where we are bringing more intelligence on the package and chiplets, it's a natural, organic way to follow through for scaling. Maybe the next would be exploiting the 3D integration, where we can have more of these layers. But the moment we also have to have hand in hand the theory to understand that does our system behave as it should when we go to these exotic ways of integration. So the DTCO and STCO will be key for that. There is so it will be key to guide what's the best integration for a given problem. Maybe there will not be a general solution. Maybe there will be very customized to the
Customized.
problem of interest.
Yeah, I fully agree. I think this is a great observation. So I think we will take just very two quick questions. So Rohit is asking if ONN is resource hungry, I think, and then how can you increase the network? That's Rohit is asking.
Oh, yeah.
Uh,
Yeah, so increasing the network, right? So modularity. So by the way, the connectivity draws quadratically. It
yeah.
explodes very. Yeah, so the moment we know how to sparsify the problem, so that there has to be also some innovation, maybe that full connectivity should not be the status quo. Maybe we should also do better at embedding the problem from the get-go, so that relaxes a little bit the connectivity requirements, so sparse connection. So there has to be that innovation. So
Yeah.
I agree. So there are innovation, as I mentioned, on all fronts
No, and
to
that's a
really scale up
good
to
time to work
show.
on this. Yeah, I fully agree.
Yeah,
This is
yeah.
a great
So
topic to
that's
work.
why we need theory people, a little
Yeah.
bit more the, computer science and even computation physics as well. But it's a nice problem to solve,
No, no,
for
absolutely.
sure.
More problem is better. So I think I'll take this last question from Louis. Louis is asking, when reading the ONN signals, is the reference based on relative phase or absolute phase difference?
Relative phase and relative and frequency, right? Because we encode both.
Yeah.
We depart from time. We relative phase difference, and that's the main way of computation, right? And yeah.
Okay.
You can also do you can also have a reference oscillator, so you can also do it with respect to that reference. So it's like your main clock. You could also there are many ways.
And all the results that you have been showing, are they from binary networks or they're also from continuous phase outputs, basically?
But so all the analogs is continuous phase. The digital is discrete because it's
Wonderful.
digital.
Yeah.
Yeah.
I think we have tried to cover most of the questions, and some of the questions I found that has been already answered during Ida's presentation. So, and the recording will be available, to be honest, in the CEDA Distinguished Lecture Series under. So I would say encourage you to review the seminar again. And, I really want to thank Ida again and all the attendees today's seminar. I think it was a wonderful seminar, and from this IEEE CEDA, I want to thank you again. Thank you very much, Aida.
Thank you. Thank you. And they can also reach out via email if there is a question that, or maybe they want to discuss further. So I will be also open to that.
Absolutely, absolutely. I think date is next week, so I think many of
Oh,
you
yeah.
also.
So maybe we'll meet some of them in person.
That is true. I'm not traveling, but many of you probably will be able to find Aida and ask questions that, okay, that we want to ask. Yeah, that's wonderful. That's very good. Take
Yes.
care. Yeah, the floor is to Jackie now. I'm done. Thank you very much.
Thank you as well.
Thank you all. We appreciate your participation and joining us today. Please keep an eye out for future lectures, and we will get this posted, like Mohammed mentioned, online. So have a great rest of your day, everybody. Thank you so much.
Thank
Thank
you
you.
very much. Thank you
Bye-bye.
all. Take care. Bye bye.
Bye bye.